In this lesson, we are going to talk about the different types of intermolecular forces that we see in molecules. Before we look at the types of intermolecular forces, we first want to understand what intermolecular forces are, and we frequently abbreviate this as IMF. So when we're looking at IMFs, what we're looking at are interactions between molecules. So intramolecular forces would be bonds between atoms. Intermolecular forces are between separate molecules of a substance. And what we get is interactions happening between these molecules that then affect their properties. So this is how the polarity of a molecule and the geometry of a molecule affect different properties of a substance. And so these interactions are the result of either charges, as in the case of ions, partial charges, as in the case of polar molecules, where we have a partial positive and a partial negative due to differences in electronegativity, or we have temporary charges. So as a result of electrons moving around, even in nonpolar substances, we can have temporary charges. Overall, intermolecular forces are generally weaker than bonding forces. So if I look at an individual force between two molecules, it's going to be much weaker than the bond happening between two atoms. However, in large biological molecules, the sum of all of those intermolecular forces can become a significant amount. We're going to look at 5 different types of intermolecular forces that happen between molecules. The 3 that we see most often and occurring most in biological molecules are the first 3. And so we're going to go through each type and see what kind of molecules we find these forces in. So the first thing are dispersion forces. So these are the weakest of all of our intermolecular forces. They're also sometimes called London forces or London dispersion forces, and they occur in all molecules, whether they are polar, nonpolar, ionic, doesn't matter. Everybody has dispersion forces. The dispersion forces are the result of temporary charges that form as the electrons are moving around in a molecule. So imagine that we're on a boat and you're out in a whale watching expedition, and everybody on the left side of the boat says, "Hey, there's a whale," and everybody runs to the left side. For that moment, there's a temporary uneven distribution of people on the boat. The same thing happens in our molecules. Every once in a while, with the electrons moving around, more of them end up on one side of the molecule than the other, and we get this temporary polarity or temporary uneven distribution of charge. As a result of that, we get dispersion forces. Again, these are very, very weak. The next type of force are dipole-dipole forces, and these happen in polar molecules and only in polar molecules. So nonpolar molecules will not have dipole-dipole forces. Notice the name of this force. We have di, which means two, and pole, which means in. So a dipole is a molecule that is polar. So if we have dipole-dipole forces, it's the attractive forces between two polar molecules, two or more polar molecules. Sometimes it's two or more of the same molecule. So we said, well, water is polar, so we have two water molecules. Or we could say water and NH3 are both polar. We could have dipole-dipole forces between those two different molecules. As long as they're polar, there can be dipole-dipole forces. The next one, which we see quite a bit of when we look at biological molecules, is hydrogen bonding. So hydrogen bonding is similar to our dipole-dipole forces. The key difference is that hydrogen bonding occurs between very specific atoms. The presence of hydrogen alone does not result in hydrogen bonding. The definition of hydrogen bonding is that a hydrogen attached to a fluorine, oxygen, or nitrogen is attracted to the fluorine, oxygen, or nitrogen on a neighboring molecule. So a hydrogen bonded to a fluorine, oxygen, or nitrogen is attracted to the fluorine, oxygen, or nitrogen on a neighboring molecule. So if we look at an example, let's look at methanol. So meth means one, it's an OL ending, so that's an alcohol. So we say we have CH3OH, and then we have another methanol molecule. So we have And I'm going to draw this a little bit differently just to make it easier to see the connection here. So we have that CH3OH, so we have two methanol molecules, and what we're going to look for is a hydrogen attached to a fluorine, oxygen, or nitrogen, so our hydrogen meets that requirement, and it's attracted to the fluorine, oxygen, or nitrogen on a neighboring molecule. So this attractive force, this hydrogen bond, occurs between these two atoms. We can also see hydrogen bonding occurring between this hydrogen and the oxygen, depending on how the atoms or molecules are oriented with respect to one another. So those are the three we see most commonly in our biological molecules. The last two are something I think they're a little bit easier to understand. So if we have an ion-dipole force, that means we have to have an ion, so something with a charge like say sodium. And we have to have a dipole, so we have to have a polar molecule. So if we had something like sodium ion in water, we would have an attraction between the sodium ion and the polar water molecule. For ionic forces, what we're going to see is that we have to have two ions. So if we have Na plus and Cl minus, we have an attractive force between them, and this is often called an ionic bond. So first we're going to look at water, which we've established in a previous lesson is a polar molecule. Now, because it's a molecule, because it has electrons, we know that it has dispersion forces, because every substance is going to have dispersion forces. We also know that it's polar, which means it will have dipole-dipole forces. And that's the result of the polarity of the molecule. So between two water molecules, there will be dipole-dipole forces. And we will also see that we have hydrogen bonding. Again, it's not really a bond, and it's not just with hydrogen, so not a great name, but that's what the name is, so we have to work with that, because we have a hydrogen attached to an oxygen, so we meet our hydrogen attached to a fluorine, oxygen, or nitrogen rule, and that hydrogen will be attracted to the oxygen on another water molecule. Get methane, which is a non-polar molecule. And as a nonpolar molecule, its only type of intermolecular force would be dispersion forces. There is not a polar molecule, so we can't have dipole-dipole bonding. We do not have a hydrogen attached to a fluorine, oxygen, or nitrogen, so we cannot have hydrogen bonding. We don't have any ions present, so we can't have either ion-dipole or ionic forces present. Now we look at our last example here. We have dimethyl ether, so we have a polar substance. We see that we have dispersion forces because everybody has dispersion forces. We also see that we have dipole-dipole forces. Because it's a polar molecule, there will be dipole-dipole interactions. Although there are hydrogens and although there's an oxygen, we will not have hydrogen bonding. In order to have hydrogen bonding, the hydrogen must be attached to a fluorine, oxygen, or nitrogen. The hydrogen is attached only to carbon atoms, and so we will not have hydrogen bonding. Likewise, there are no ions, so we will not have either ion-dipole or ionic forces. So here's one for you to try. Will NH3 have dispersion forces? It will have dispersion forces because all molecules have dispersion forces. Will NH3 have dipole-dipole forces? Yes, it will have dipole-dipole forces because it is a polar substance and therefore will have dipole-dipole forces. And will NH3 have hydrogen bonding? Yes, it will have hydrogen bonding because we have a hydrogen attached to a fluorine, oxygen, or nitrogen, and that hydrogen will be attracted to the nitrogen, or in this case, or a fluorine or oxygen on another molecule. We don't worry about ionic forces or ionic dipole forces in this substance because there are no ions present. We would have to explicitly show a charged species in order to say there's an ion present in the sample.